So in the last video, we had just written down this expression, and I talked about the fact that this might not be the best case, because while we do know what the initial velocity is and we know what the acceleration, sorry, we don't know, we want to know what the initial velocity is, the only thing we know about for sure in this whole expression is the acceleration. We introduced this is an unknown, this is an unknown, and this is an unknown. So that's three unknowns in one expression. Here we have two unknowns in one expression. Up here we have two unknowns in one expression. We don't have enough known quantities, right? You can't solve three equations with these few unknown quantities. You still have unknown quantities at the end. But instead of using this particular kinematic equation, there's another one that kind of circumvents this stuff, that kind of gets back at things that we already know something about. Notice this doesn't have any mention of the final velocity. That's actually a quantity that we know. So if we take the time and use an expression from the text that's derived from all these simple expressions for constant acceleration, we know that the final velocity squared is equal to the initial velocity squared plus 2a delta x. All right. Now, delta x in this situation would be delta x, the displacement during the braking. All right, and this is still positive, even though we're going to plug in a negative value for the acceleration. Now we know that the final velocity here is going to be 0, and the initial velocity is an unknown. Right, so we have two unknowns here, we have two unknowns here, and two unknowns here. So that should provide us with a few enough unknowns that we can actually now solve this expression. Right. So we have, if we kind of collapse all these things together, let's see how that pieces out. In order to plug it into, we're going to plug it into everything into this expression up here. Right, so the way we do that, we multiply delta t react by both sides, and we get into this expression. Sorry, I'm going to draw a little arrow. Right, we're going to get the initial velocity times the reaction time plus the displacement, right, which is Vf squared minus Vi squared divided by 2a. And that's going to be equal to the total displacement. All right. So looking at this expression, we know that Vf is equal to 0 meters per second squared. And we can actually plug in all of the other values that we know in this expression, because there's quite a few. We're going to bring the total displacement back over here to the left side, and I'll show you why that is in a second. So we're going to have minus, did I get through this right? We'll get minus 1 over 2a times Vi squared plus delta t react times Vi minus delta x tot equal to 0. Now, we only have one unknown in this entire expression. All these other constants are something that we actually know. And you may or may not recognize the form that this is in, because it's a little bit weird. Usually we might see an expression like this that would fit the general expression of ax. This is going back to math terms, right? Ax squared plus bx plus c equal to 0. Now, if you had this expression, you'd be like, oh my gosh, yeah, we can use the quadratic formula. And the same thing is true as for this expression, right? In this case, a is negative 1 over 2a, b is equal to, actually, I think that this is most often done with lowercase letters, right? So maybe this capital letter doesn't look quite as familiar. Yeah, I'll just leave it with capitals for now. Where capital B is delta t react, and c is equal to minus delta x tot. And you can plug those all into an expression that will solve, where x here is just the initial velocity. So we can find solutions for the initial velocity that are equal to, oh my gosh, minus, that would be minus, I can't remember what the quadratic formula is, minus b plus or minus the square root of b squared minus 4ac divided by 2a. That might not be perfectly correct. I think that's right. And this so it gives us two solutions for the initial velocity, and just plugging in all these values. That might seem kind of messy, but this is exactly the way we can do it. You could multiply everything by 2a and plug in what those particular numbers are. But once you reach this point, this is just mathematics, right? We plug in all the numbers, we get a particular numerical value, and that should work out. The secret to this problem, and it's not really much of a secret, but the challenging part is trying to figure out how we can get a solvable answer. And the question is starting with equations that limit the number of unknown quantities that we have and maximize the number of known quantities that we have to put into the problem. And I think this is particularly tricky because one of those known quantities is that the final velocity is 0. It comes to rest. And so we need to leverage that information in solving the problem. So I hope this was helpful.